Hello, everyone. Welcome to the Theoretical Computer Science seminar at Jagiellonian University. Today we have Ross Kang from University of Amsterdam. Ross is a well-known mathematician in the area of extremal combinatorics. He did his PhD in Oxford. Then he did various postdocs in McGill, Durham. He was working in Utrecht University, then in Radboud University, and this year he moved to Amsterdam. Ross is also one of the founders of a very successful series of workshops called the SPARSE Graphs Coalition. And today he's going to tell us about coloring graphs with sparse neighborhoods.
Thanks, Bartok, for the invitation. Yeah, thanks everyone for coming to attend this seminar. I'm very honored to tell you about some of my work. I'd like to tell you about coloring graphs with sparse neighborhoods, and this is a purposefully vague title, and it includes a lot of different interpretations. But I'm going to focus on one of the, I would say, most important interpretations of this title, and it's going to include various joint works with Ewan, Owen, Rémi, François, and Jean-Sébastien. But before I start, I'd like to just sort of preview the talk with some of the broad brushstrokes. And it also describes what I've been interested in, especially in the past 5 years. I guess the main question is another vague idea, which is this question here. When you forbid edges in a graph's neighborhood, then what kind of global graph structure can you deduce, especially for large graphs? And one can think of this as fitting within the local to global kind of idea within mathematics, because having no edges, having no edges in your neighborhood is a kind of locally checkable condition, and then we're interested in more global conditions after that condition is imposed. And of course, this is about triangle-free graphs, actually, this question that I've just posed. And this goes back a really long way. It goes back to the work of Mantel, Duran, RAMSEY, there's lots of, and also Tut. And it's really played a very strong role, of course, in combinatorics and beyond. And it's still a very interesting question in the present day. And I work quite often with a sequence of graph parameters, which I'm sure you're all familiar with, but just to flash them on the board. So the first one in this sequence is the Glick number, the size of the largest complete subgraph. And the next is basically the independence number, so the size of the largest independent set, but inverted. So it's in this form, it's called the Hall ratio. And next in this sequence of inequalities is the fractional chromatic number, and then the chromatic number and the list chromatic number. And at the end of this sequence, we have the maximum degree plus 1. And I think you all know that these parameters are all organized in this sequence of inequalities, and it also fits in a general trend in combinatorics. So if you think of the independence number as sort of finding a sparse object, then quite often the case you want to then find a fractional packing of those sparse objects. So say through the fractional chromatic number. And then after that, maybe you want to find a perfect packing of those sparse objects, say through the chromatic number. And then you also want to have even more organized structure, like the list chromatic number. And so in much of my work in the past few years, I'm interested in sliding back and forth along this sequence of graph structure. Okay, another theme that plays a part, especially in this talk, of course, is the probabilistic method, and then a cornerstone of the probabilistic method, as you all know, is the Lovász-Lókol lemma. And in a nutshell, it says that it says the following. Well, first of all, if you have a collection of n mutually independent events, all having probability at most p, then trivially, just from first year probability course, you know that the probability that none of these events occurs is at least 1 minus p to the n, which in particular is positive if p is strictly less than 1. But the Lovász-Lókol lemma says that if you can relax this mutual independence condition to some sufficient local control on dependency, while still continuing to have the conclusion that the probability that none of these events occurs is positive. And this is Lovász-Lókol lemma, right? So if each of your events is mutually independent of all but 1 over EP of the others, then you still maintain this conclusion of positive probability of simultaneous non-occurrence of the events. Another kind of theme that plays a role in the work I'm going to talk about is called stochastic local search. And the idea is that suppose maybe you want to look at algorithms that can find your object in question, your flawless combinatorial object in question, and you want it to be stochastic, and you want it to only use some local modifications in its search. Then there's some way of making precise the question, what are its theoretical limits? And this, of course, as you probably many of you already know, is essentially what's behind Moser's entropy compression method, which yielded the constructive form of the Lovász-Lókol lemma. And this method has had a big impact, not just in theoretical computer science, but also in terms of the analysis of stochastic algorithms, but also in terms of the actual quality of combinatorial constructions that result from these algorithms. And then another theme that I'd like to weave in, hopefully by the end of this talk, is the so-called hardcore model, which I'll try to talk about more later. It's essentially a very nice probability distribution over independent sets in a graph. So that I just wanted to flash these sort of cartoons just to give you an idea of what's coming, but also to hopefully let you bring away some key ideas that might come into play later. So are there any questions so far? And please feel free to interrupt me in case you have any. So I'd like to kind of gently introduce the set of problems that I'm interested through basically chronological order. So I'm going to start with the RAMSEY numbers. Just to remind you, the RAMSEY numbers, R, K, L, are defined to be the smallest n, such that in any red-blue edge coloring of the complete graph on n vertices, you're guaranteed to have a red clique on k vertices or a blue clique on L vertices. Of course, RAMSEY himself proved he needed this he needed these Ramsey numbers, and he needed to show that they're finite for some Hilbert problem in the 1930s. But later, Erdős kind of latched on to these Ramsey numbers, and now their finiteness is sort of a symbol for this paradigm. The idea that in any large enough system, say a red-blue edge-colored Kn, then you're guaranteed to have some highly ordered subsystem, such as a monochromatic clique of a certain size. And when you think of this paradigm, then what comes to what comes to mind is that these Ramsey numbers essentially, or at least the Ramsey numbers -1, quantify the most disordered systems. So if you want to find, so you want to find sort of examples that certify lower bounds on these Ramsey numbers, is if you put it in this way, then it's sort of obvious that you're looking for graphs with a high amount of randomness. And of course, that was what Erdős realized in 1947 and basically defined the random graph for this purpose. But I'm not going to be so Erdős was concerned with these diagonal Ramsey numbers, but I'm not going to be concerned with that case, but instead I'm going to be interested in the so-called off-diagonal Ramsey numbers, R3K, which I phrased as follows: the largest n, such that in any red-blue edge coloring of Kn minus 1, the largest n such that there is some red-blue edge coloring of the complete graph on n minus 1 vertices with no red triangle and no blue clique on k vertices. This is sort of the contrapositive formulation of it. But you can also think of it in this way: R3K is the minimum order of a triangle-free graph, G, that guarantees G to have independence number at least K. In other words, to have an independent set of size K. So here's just a very quick overview of the state of the art of what is known about these Ramsey numbers R3K, especially when K is large. After a lot of effort, so I'm sort of brushing under the carpet quite many years of work on these numbers. There was a breakthrough by Aitai, Komosh, and Semerdy in 1980, who showed that these Ramsey numbers are bounded by order k squared over log k. Very shortly after that, Shearer streamlined their result in terms of getting an asymptotic constant of 1 times k squared over log k as k goes to infinity. And Aitai, Komosh, and Semerdy's work was seminal because it actually introduced the rudimentary form of the so-called semi-random method. And for a long time, there was even more work still, but for a long time it remained open what would be the right order for the lower bound. And finally, using a much more sophisticated form of the semi-random method, Kim managed to get the right order of growth, again k squared over log k with an unspecified constant. And Erdős, Suin, and Winkler shortly thereafter actually conjectured maybe the best way to try to get at the right constant, or some form of the right constant, which is through the so-called triangle-free process, which I guess you probably all know of, but let me just remind you what the triangle-free process is. It's where you start with n vertices and you take a random ordering of all possible edges, and start trying to add them one by one in sequence. And then whenever you run into a problem, so you could possibly add the third edge of a triangle, you just ignore it and throw that edge away. And this, of course, is a very difficult random process to analyze, but Bowman found a very nice way to do so using the differential equations method. And then two teams in a very large pair of works managed to analyze this process almost to its endpoints and managed to get a leading constant in the lower bound of 1/4. And I guess some intuition for why this 1/log correction factor is again about thinking about these Ramsey numbers kind of describing the most random or most disordered system in the context of this problem. And then there's actually a kind of a strong affinity between the triangle-free process and the random graph. And that's intuitively maybe where you should expect this log k on the bottom to come from. But what I'm going to be focusing on mostly is this first upper bound on the Ramsey numbers, but actually a slightly different form of it, which I've put here. So it's a statement that says that the independence number for any triangle-free graph G on n vertices is asymptotically at least n log delta over delta, where delta denotes the graph's maximum degree. And it's just a very simple exercise, just separating based on the vertex of maximum degree to show that this particular bound on the independence number implies the upper bound on the Ramsey numbers R3K. So I'm going to be focusing on this particular statement for most of the rest of my talk, actually. And one thing I want to mention right away is that okay, so first of all, let me invert it again. So in terms of the Hall ratio, it looks like this. And then one thing I want to mention straight away is that this particular statement is sharp up to a factor 2, an asymptotic factor 2. And that comes from analyzing the random regular graphs and showing that with positive probability, they have 1/2 of this value as the Hall ratio. Okay, so, but I said I wanted to talk about coloring graphs, and so far I've only been talking about independence numbers in graphs. And so now I want to talk about coloring them. So like I said before, coloring can be thought of as like a perfect packing of independent sets, and then you have this sequence of kind of global structural parameters in graphs. So I mean, it doesn't hold in general that you can do this, but for triangle-free graphs, you can ask how far along the sequence you can go. And there was a breakthrough. So first of all, yeah, there's two breakthroughs. So one was due to Johansen in the 90s, again, using this kind of, using the semi-random method or Rödel nibble, managed to show that the chromatic number of triangle-free graphs is bounded by delta over log delta with an unspecified leading constant. And then there was another breakthrough, which was more recent and was shortly before I started working in this area. It was due to Malloy in 2019. He showed that the chromatic number can be bounded by an asymptotic factor of 1 times delta over log delta. And the asymptotics is always as delta goes to infinity. And what was really nice about this work by Malloy is, while originally Johansson's proof used this kind of quite technical Rodel nibble machinery, Malloy found a way to leverage this so-called entropy compression method to find a much shorter proof of a stronger statement with the kind of correct leading constant matching Schirr's bound. And the proof, I'm sure many of you in the audience already know this proof, but it's very nice. It's about 5 pages long, and it was a very big surprise to see not only the elegance of the proof, but also the strength of the result when you think about Ramsey numbers. So one thing that I would like to hopefully prove to you by the end of this talk is this result, which is about the fractional relaxation of the chromatic number. So the fractional chromatic number being bounded by the same asymptotic quantity, delta over log delta. And I guess this might seem like a bit of a mathematical joke or something, right? Because this is a later result with a weaker statement, if you think about this sequence of structural parameters. But what I hope to convey to you is that so there is a good reason for doing this. So one is that we use this hardcore model to find an even shorter proof than Malloy's without using any local lemma machinery at all. And it's a proof method that has proven to be quite versatile and adaptable to many aspects of the title that I gave. So many aspects of graphs with sparse neighborhoods.
Excuse me, I have a question.
Yes.
You said that this Malloy result is about the chromatic number, but your slide says it is about choosability.
It's also, yes, it's about the list chromatic number. It's also about the correspondence chromatic number, and yeah.
Okay, so it is even stronger.
Yes.
And how about Johansson's? Was it also about choosability?
It was also about choosability, yeah.
Okay,
so
thanks.
The natural framework within which you can work with Rodel nibble type arguments. Thanks for the question. Okay, so this is the plan that I hope to get to by the end of the talk. But first, I want to talk about that specific interpretation of graphs with sparse neighborhoods that I want to emphasize today. And that's on this slide. So let's just observe that having no edges in any neighborhood is the same as triangle free, of course. What if we relax this a little bit? And let's just say that we have at most a certain number of edges induced in any neighborhood instead of just 0. And let's quantify this by some parameter. So let's say that G has local density at most eta if for every neighborhood you have at most eta times delta choose 2 edges. So delta choose 2 is the maximum possible edges you could possibly have theoretically, and let's have as a condition eta times that, an eta proportion of that theoretical maximum. And so if you take, so you can think of eta being a function of delta, and if eta is around 1 over delta squared, then this corresponds very closely to the triangle free case. And if you take eta to be 1, then this, of course, has no restriction whatsoever, right? And so this should be corresponding to the general case where you expect this trivial bound of delta plus 1 as your upper bound. But let's just to give a little bit more intuition about what this means, let's look at an example. Let's just look at a clique of size square root eta times delta. And then we'll add some pendant vertices to make sure that delta is indeed the maximum degree of the graph. It's easy to check that this actually has local density at most eta. And then if we plot this, basically this is just a plot of root eta from 0 to 1, even though the margins look very funny. So this is just basically a plot of what it should look like for the clique. And I should also mention that if you want to like boost eta for some reason, then it suffices to blow up all the vertices by a clique. Okay, but this is just to get you in the mood or something. So now the question is, what about the best chromatic number bounds in graphs of local density at most eta? And so far we focused on the best chromatic number bounds where eta is equal to 1 over delta squared. And you can ask the same for any choice of eta. And why would, I mean, I probably don't have to ask you why you would, but let's, for the sake of it, just ask ourselves, why would we want to look at this particular problem? Well, of course, there's many graph coloring problems where you can establish such a condition, where you have graphs with a given local density. And so you can apply such results in many parts of graph, well, at least chromatic graph theory. And this idea was already thought of in the 90s. And I want to focus first on the eta being small case. So in the eta being small case, or very close to the triangle free case, then Alon, Krivolovich, and Zudakov already noticed by bootstrapping Johansson's result that you could get a more general result for this specific setting. And they essentially showed the bound that's given on the slide, that that you can get an upper bound of roughly delta over log of some constant divided by root eta for any graph of maximum degree delta with local density at most eta. And this was also developed further by Wu in the list coloring setting, and then quite recently by Aklioptis, Iliopoulos, Sinclair, where they applied what they call the stochastic local search framework to try to tighten this bound as much as they could. But still they were off by some constant factor, and with our technology, we managed to tighten this leading constant factor to maybe what you could call the right constant, a leading constant of 1. For eta strictly, so eta has to be vanishingly small, but still as a function of delta. And what's important to notice is that if you plug in 1 over delta squared here for eta in this bound, then you will again get a delta over log delta with a leading asymptotic factor of 1. And the other thing to mention is that if you look at random regular graphs, and then you blow them up by cliques a little bit, then you can see that this bound is actually sharp up to a factor of between 2 and 4 for the range within which eta is allowed to vary. But there's one problem with both of these results. So if you look at the eta equals 1 valuation for these statements, neither of them give anything for the eta equals 1 case. And we should expect it to kind of, yeah, so for sanity, we would like it to smoothly go towards delta plus 1, but unfortunately, we don't have that so far. But I wanted to mention, so that goes to the other case for which you can look at this problem, which is when eta is some fixed constant between 0 and 1. And you can still ask yourself, right? So, and this includes the case that's very close to 1. So can you always get a non-trivial improvement on this trivial upper bound delta plus 1? And again, so why would you ask this? Again, this is a problem that sort of appears in other graph coloring contexts. And for instance, it's applied for work on Reed's conjecture. It's also applied in work on the Erdős-Nesterov conjecture, which I'm not going to go into more of. But what Molloy and Reed already showed again in the 90s is that the answer is yes. They showed that for any eta strictly less than 1, if you have a graph of maximum degree delta and local density at most eta, then you can find some epsilon in terms of eta strictly bigger than 0, such that the chromatic number of G is always at most 1 minus epsilon times delta, provided delta is large enough. Yeah, and they use this to get progress on the Erdős-Nesterov conjecture. And they were only interested in getting some constant epsilon. So they didn't really do much optimization. They got this, roughly this type of lower bound on epsilon in the statement. It was quite some time before Brun and Jos attacked the problem, and they got a big improvement on the estimate for epsilon. So they got it up to 0.18 times 1 minus eta or so. And then shortly after, Bonomi, Parrott, and Postel improved this by another 50%. And yeah, so we came into this and actually using ideas that were already suggested by Molloy and Reed in their paper. We managed to, but also using a lot of the ideas from the 2 earlier works. We managed to get an estimate on epsilon of roughly half times 1 minus eta. But let me recall this example that I gave to you, the cliques of size root eta times delta. What those examples actually show, right? They're cliques, so they have as a lower bound for their chromatic number, they have root eta times delta. So actually, if you take eta to approach 1, these cliques of size root eta times delta actually show that epsilon has to be at most roughly 0.5 times 1 minus eta as eta goes to 1. So this is infinitesimally sharp result is what we obtained, but still it's something to say. But let me just kind of summarize these 2 sets of results on one slide. Both of them are related to the same question, but in different regimes. So here in red is this result with Owen and Remy. In black are the clique examples. And it's actually this corner, there should be like a red dot, which encompasses this result with Ewan and Francois and Jean-Sébastien. So what I wanted to highlight is, so we have this local occupancy method for this first listed result, but it doesn't get you out of this corner, unfortunately. Somehow the methods that we use, which I'm going to try to explain to you a little bit about shortly, they don't get you out of this corner. So there's a big gap between this red line and what's happening for graphs close to being triangle free. And that, I think that's a very nice class of problems, which so if you have any ideas, I'd be very open to hearing them and discussing with you. So let me just pause a second. So yeah, we have I guess another 10 minutes or so, but let's pause maybe in case you have any questions so far.
Can you hear me?
Yes. Hi.
Yes, I just have a small question about this this parameter eta, right?
Yes.
So you define this local density as the number of edges in your neighborhood or triangles, I guess, is less than eta times the maximum number of edges that you can have.
Yes. Yes.
So it's delta choose 2, right? And
yeah.
I just thought that a more well, at least to me, it seems like a more natural way would be number of vertices in your neighborhood, right? Choose 2 instead of delta. So it is a little bit more restrictive, a little bit stronger, I guess. So I was wondering if it happened to be studied already, or is it more interesting or not, or maybe just not that much more interesting than this parameter that you already have?
So just based on my first, so it hasn't been studied in that precision, but well, actually it has. So we have for all of these results here, we actually have local results. So we have results where we're basing our list sizes based on the degree of that particular vertex. And then the density bound is also based on the degree of that particular vertex. Mm-hmm. So we've already kind of covered that stuff. But one thing to notice is that for these results, like I said, they're kind of matched by graphs that are regular.
Mm-hmm. Yeah, I see.
So you don't expect to actually get anything stronger when you, yeah. So I don't know if that answers your question. In other contexts, it might make more sense, but in this particular extremal context, then because you kind of expect your extremal examples to be regular, then it doesn't.
Right. Yes. Mm-hmm. Thank you.
Okay. Yeah, so what I want to do next is unless there are more questions, what I want to do next is try to give some more intuition behind this first result about the case that is close to triangle free. And I also promised to prove a redundant result. So yeah, that's my plan for the rest of the talk. And in order to carry out this plan, I need to introduce to you more formally the hardcore model. And okay, so I have this cartoon, but that's just really a cartoon from Wikipedia. The hardcore model is defined as a probability distribution over the set of all independent sets of a given graph G. And it's got a very nice form. But more formally, the hardcore model is given with a parameter lambda, which is called the fugacity. And the hardcore model is a distribution over this set I, such that a random set from this distribution satisfies for every independent set S that the proportion of, sorry, the chance of taking that set S is proportional to lambda to the number of vertices in S. And, you know, more precisely, the probability that our random I is equal to S is equal to lambda to the order of S divided by a normalizing factor to make it a probability distribution. And this normalizing factor is just the sum of all the probabilities over the whole space. And this normalizing factor Z is called the partition function of the hardcore model. It's also called the independence polynomial. And so I'm phrasing the hardcore model in terms of probabilities, but you can actually also think of it in terms of polynomials. And then if you think about it in polynomials, then there's all these tools that people have started using, especially here in Amsterdam, with analysis or whatever, algebraic tools. But I'm thinking of it in terms of a probability distribution. And the reason is this very nice property called the spatial Markov property. And for a given independent set S, let's call a vertex U occupied if U belongs to that set S. And if a neighborhood, so if U has a neighborhood which doesn't intersect S, then we call U uncovered. So let's say these big black vertices are in my set S, so they're occupied. And these white vertices here, they don't have any neighbors that are occupied, so we call those are uncovered. Is everyone clear on this admittedly kind of awkward notation? Okay. The spatial Markov property is based on these this notation. So let's take some random independent sets from the hardcore model at fugacity lambda, and then let's look at some set X. So this blob, let's call this the set X to some subset of the vertices. Then let's reveal what happens outside of X. Okay. So suppose then we get these three vertices somehow. Then let's look at the set of externally uncovered vertices. So, right, we're only revealing what happens outside of this set X. So it doesn't really, we don't really see anything that happens inside, but these two vertices here are externally uncovered, right? So they don't have any, so in particular, the only neighbors that are outside of X, they're both not in my independent set. Then if you now reveal what happens inside the set X, you can then that is actually another hardcore model on the externally uncovered vertices inside X, and it has the same fugacity as well, lambda. So what I mean, in a nutshell, what this spatial Markov property says is that you can sort of cut away what happens outside and inside. You can sort of make those two experiments independently somehow in a precise way. And so yeah, this is it's a very nice property of the hardcore model, and this is like the main engine behind this framework that we've introduced, the so-called local occupancy framework, or the local occupancy method. So I'm going to try to illustrate the use of this method, in particular for triangle-free graphs. But what is this? What do I mean by local occupancy? Well, I mean this precise thing. So this is kind of the key property that we take advantage of in this method. So we have some parameters A and B. We say that some distribution over the independent sets has local AB occupancy if uniformly for every vertex V, A times the probability that V is occupied plus B times the expected number of occupied neighbors is at least 1. And so this method actually hinges on establishing this property, and let me now kind of illustrate this in the special case of triangle-free graphs. So in this method, which we have a more general form of, what you have to do is take 2 steps. So one step is this step A is to find some probability distribution, in particular the hardcore model works in this case, that has local AB occupancy for some specific A and B that depends on lambda and the maximum degree delta. And the second step is, so if you have a probability distribution on the independent sets with this property, then actually almost directly you get a fractional coloring bound of A plus B times the maximum degree. So once you've completed these 2 steps, it's just yeah, you could call it an exercise maybe for a very advanced undergraduate in analysis to minimize A plus B times delta subject to this condition. And when you do that analysis, then you will see for the triangle-free case that the fractional chromatic number is at most delta over log delta with a leading asymptotic constant of 1. And so for part B, actually, I'm not going to go over any of the details of part B. If you want, you can read the book of Malloy and Reed. There's actually one small section devoted to this, where they prove the fractional rebound. But it's a more general phenomenon, and yeah, and the idea is essentially to use the probability distribution on the independent sets in an iterative way, a greedy way, and then delete any vertices that you've already filled up. So I'm going to focus on the step A in the special case of triangle-free graphs G. And hopefully this will give you some inspiration or some idea of what's going on. And in order to establish this step A, so I want to find that the hardcore model has local AB occupancy. It relies on 2 facts. Facts 1 and fact 2. Fact 1 is, what is the probability that V is occupied given that V is uncovered? Well, in order to establish this fact, essentially we put a blob around V. So my set X, I basically defined to be my vertex V. And then the conditioning says that it's uncovered or externally uncovered. And so the probability that V is occupied is just lambda to the 1. So that V is an independent set, divided by the total possibilities, which is 1 plus lambda. Yeah, I'm sorry, I didn't bring my tablet, so I can't draw it, but it's really just putting a circle around the vertex V. And fact 2 is what is the probability that V is uncovered, given that V has exactly J uncovered neighbors. So this again uses this local Markov property, the spatial Markov property, where you put your blob around the neighborhood of V. And then you have exactly J externally uncovered neighbors, and you have a triangle-free graph. So you want all those J uncovered neighbors to simultaneously be not occupied, and it's not occupied with probability 1 divided by 1 plus lambda because of triangle freeness raised to the J. So both of these facts are simple consequences of the spatial Markov property. And these two facts combined are all that we need to get at our local AB occupancy. And let me just run you through that kind of quickly, actually. So the probability that V is occupied is just equal to the probability that it's occupied and uncovered. Just trivially, it has to be uncovered if it's to be occupied. And then we can use fact 1 immediately using a conditional probability. And then you can divide the probability that V is uncovered according to the number of uncovered neighbors J. So by fact 2, this equality follows. And then we notice that this summation is just an expectation of 1 minus lambda to the minus J, where now we treat J as a random variable, counting the number of uncovered neighbors of V. And then by convexity, we can move the expectation into the exponent. Okay, so that's basically getting an expression or a lower bound for the probability that V is occupied. And then for the expected number of occupied neighbors, we use linearity of expectation. And we use fact 1 again. And again, we get two expressions or lower bound expressions for the two quantities that we're after. And now we can plug it into the expression that we want to bound below by 1. As follows, and then we need to do some optimization, and we just notice that the expectation of the number of uncovered neighbors of V is just some positive real number, and so we can optimize over all such numbers, and then again by convexity you get some expression, some analytic expression, and we want this expression 1. So what I've shown is that fact 1 and fact 2 implies that A plus the probability of B being occupied plus B times the expected number of occupied neighbors is at least this expression, and this expression should be at least 1. So again, you just have to do this optimization, minimize A plus B times delta due to stat B, subject to this nasty expression being at least 1. And yeah, okay, so that's again some exercise for maybe Maple or Mathematica, and you will get that delta over log delta is a good good optimization for this. Okay, so that was just a very quick overview of the local occupancy method, and it also applies to other settings where you can think of coloring graphs with sparse neighborhoods. But I want to, at the end of this talk, point out some barriers to this method, which so we've managed to kind of cover a lot of cases in graph coloring and in well, I guess kind of RAMSEY theory. But there's still a lot of work to do and a lot of challenges. Of course, all of our methods do not beat the Shearer bound with a leading factor of 1. And I just wanted to point out this predecessor work due to Davies, Jensen, Perkins, and Roberts, which showed that the expected size of an independent set is at least n log delta over delta. And this is sharp up to a factor of 1. But what's kind of the most mysterious part of this work is this question of CARP from the 70s, where they were trying, so CARP was interested in knowing about the kind of average case behavior of the independent set problem. And so already in the 70s, you know, people wondered, is there a polynomial time algorithm to find an independent set in G(n)½ of size strictly more than log base 2 of n, with this leading factor 1 plus epsilon for some fixed epsilon. And of course, there's an analog for this for the random regular graph, which looks like this. And this is also a kind of a barrier for us. It's an algorithmic barrier, which we are not able so far to surpass. And one way that people have conjectured to get around this, Davies, Jensen, Perkins, and Roberts, is perhaps if you're looking at the ratio between the average size of an independent set and a maximum one. But this remains wide open. So I'd like to thank you for your attention and remind you of the kind of key open problem that I wish people could work on and make progress on. Thank you for your attention.